Okay, hi everyone. Welcome back to the Iowa City Math Circle. This week we'll be talking about angles and triangles. Give us a second before we get started. Okay, so first we'll do a brief overview of angles. Okay, so let's start with the definition of a ray. So a ray is a line segment that is extended infinitely in one direction. So let's say we have a point A and a point B. Then ray AB would be this segment that starts from A and then extends infinitely in that direction. And we would write it by writing AB and writing an arrow above it. Okay, now let's talk about angles. So an angle is the union of two rays that share an endpoint. So let's say we have a point there, a point here, and a point here. And we have one ray going that way and another ray going that way. So this point here would be called the vertex of the angle. And each of the two rays is a side. So this one is a side, and this one is also a side. And we can also use line segments as part of an angle. So we could just take this segment here and this segment here, and they would also be sides of the angle. So when we have an angle at points A, B, and C, we can write it as angle A, B, and C with this symbol right here. And then the measure in between the two sides, we call it the measure of the angle. And as we see here in this angle, it's alpha. And alpha can either be in degrees or radians. But for this handout, we'll just talk about degrees. So we can say that angle ABC equals alpha degrees. Okay, so let's talk about some specific types of angles. So a straight angle is one that has a degree measure of 180. And that would just be something like this, where all 3 points that define the angle are on one line. And as you can see, that means that it's just a straight line, and it would have a degree measure of 180 degrees. A right angle would be half of a straight angle. and it has a degree measure of 90 degrees. And right angles are always denoted with this squarish symbol as opposed to this circle for other angles. And then a reflex angle is one that has a degree measure that's over 180 degrees. So let's say we have this angle here. So we could have an angle on this side of it, but for a reflex angle, it would actually be on the outside. So the degree measure of this would be 360 degrees, which is what a complete rotation is, minus whatever is on the inside. So the measure of this reflex angle here would be 360 minus alpha. Okay, and then we'll just do a few quick definitions real quick. So two angles that have the same measure are called congruent angles. And two angles are complementary if their measures sum to 90. So for example, if we have this right angle here and we draw a line through it, these two angles here are complementary. And two angles are supplementary if their sum is 180. So if we have this straight angle here and we split it into two, then these two angles will be supplementary. An angle bisector is a line through an angle that splits the angle into two congruent angles. So let's say we have this angle here, and this is the bisector if it splits the angle into two angles such that these are the same. Okay, and then any two intersecting lines that form a right angle are called perpendicular. So let's say we have these two lines. If they form a right angle here, that means they're perpendicular. And you often see that this upside down T is used to denote perpendicularity. And it's also worth mentioning that we use two double lines to mean two lines are parallel. And then an angle that's between 0 and 90 degrees is acute. So this is an acute angle, and this is obtuse. So just some review of some geometry terms. So if a line intersects a pair of parallel lines, so parallel lines are two lines that never intersect, like G and I here. Then there are several pairs of congruent angles. So beta, 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 beta. These all have the same measure, and same for alpha. And then if we have these two parallel lines G and I, the transversal would be the line that's going through them here. So it's the line that intersects two parallel lines. Let's clean this up a little bit. And then vertical angles will be two angles that are opposite each other. So for example, in this part here, where we have two intersecting lines, alpha and alpha are vertical angles since they're on the opposite sides of the intersection. And because they're on the opposite side of an intersection, that means that they will have the same measure. So in general, we can have this theorem here where two lines are parallel if and only if any transversal intersecting both lines is incident at the same angle. So if we know that beta and beta here are the same, then we can say that these two lines are parallel. Likewise, if we know that two lines are parallel and we draw a transversal, all of this has to be true. So now let's move on to talking about some basic properties of triangles. So first we'll go over why the sum of the interior angles in a triangle is 180 degrees. So let's draw our triangle right here. And the first thing we'll do is we'll also draw a parallel line at the top. Okay, and then let's also give the triangle a few degree measures. So first, let's let that one be A, B, and C. So note that we have a few transversals here. So this line is a transversal, and the other one is also a transversal. So that means that we can find some congruent angles. So the angle that's congruent to B would be here on this side, and an angle that's congruent to C would be here on the other side. And then if we add them up, we notice that they make a straight line with degree measure 180. So that means A plus B plus C equals 180. And since this is also the sum of the interior angles in a triangle, we finished the proof. So now let's take a look at this checkpoint where you should prove that the sum of the exterior angles. So that would be something like this. These are all of the exterior angles. You should try to prove that they add. Okay, sorry about that. I'm back now. Did anyone make any progress on the checkpoint? Do you guys want some more time to work on the checkpoint? Let's talk about it in like a minute. Okay, did anyone get the proof? Looks like Florence has something. Right, so if the sum of the interior angles is 180, Um, let's label some of the measures for convenience. A plus B plus C equals 180. And the sum of the exterior angles will be 180 minus A plus 180 minus B plus 180 minus C. And we can rearrange this to make it 3 times 180 minus A plus B plus C. And as we know, A plus B plus C equals 180. So we plug that in there, which gives us 3 times 180 minus 180 equals 360. Okay, and then the proof for an n-sided polygon is pretty much the same. It's the same principle where we sum up the interior angles and use that when summing up the exterior angles to cancel out and get 360. So you can try that on your own time if you're interested. So also we have this theorem that says, oh, let me draw a triangle first. So if you have A, B, and C, such that A is greater than B is greater than C, and that means that the opposite sides, so side A would be opposite angle A here, same for B and C. Side A would also be the greatest, B is also the greatest, and C, no, B is less than A and C is less than B. So this is something that you can prove with a law of sines. So we won't go into too much detail, but basically we know that A over sine A equals B over sine of B equals C over sine of C. So that's what makes this inequality true. Excuse me. All right, so now let's talk about altitudes. So the altitude of a triangle is, let me draw another triangle now. It's a line segment that extends from one vertex of the triangle and hits the opposite side at a 90-degree angle. So let's take this point here. We drop an altitude down to this side here at a 90-degree angle, and this is an altitude now. So every triangle has 3 altitudes, one from each vertex. And sometimes these altitudes can be outside of the triangle itself. So for example, if you look at this vertex, its altitude is going to be like this. And same for this vertex, its altitude might come out like that at a 90-degree angle. So now that we know about altitudes, we can also talk about area. So as you probably know, the area of any triangle is half times BH, where H is the length of any altitude and B is the base where the altitude hits. So let's try to prove this real quick. So we have this triangle with altitude H and base A. Now we can draw a rectangle to inscribe the triangle such that the base A is one side of the rectangle and the height of the rectangle will be H. So you can see how the altitude splits this rectangle into 2. And in each rectangle, the other side splits the rectangle in half. So this is half of the triangle, half of the rectangle. And on this rectangle, this is also half of the rectangle. So what that means is that the area of the triangle will just be the half of the area of the rectangle. And the area of the rectangle would be AH, So half of that would be half AH. So that's how we get the area. So now let's take a look at this checkpoint. And let's talk about it in about a minute. Send your answers in the chat in the meantime. Here's a hint. You can use the area formula for this. Area equals half BH. Okay, anyone have an answer? Also, I'll just mention real quick that we have a Kahoot at around 3, and before that we'll have a 5-minute break. So that's like the schedule for today. Okay, let's talk about it now. So we have 2a equals 2a over b equals h. And remember that h is the altitude. So to get all the altitudes, we just divide 2a by the bases, which are the side lengths. 2a over 4, 2a over 6, 2a over 7. So the shortest altitude will be the one that's divided by the biggest number. So this is the shortest one. The longest altitude is the one that's divided by the smallest number. So that would be this one. And we're trying to find the ratio between them. So that's 2a over 4 over 2a over 7. And it should be 7 over 4. Okay, so now let's move on a little bit to right triangles. And as you can probably guess, a right triangle is a triangle that has a right angle. So if we have a right angle and make it a triangle, it's a right triangle. So the hypotenuse of a right triangle is the longest side of the triangle. And that's also the side opposite the right angle. So this is the hypotenuse. The two legs of a right triangle are the non-hypotenuse side. And they are the legs that make the right angle. So this one is a leg and this other one is a leg. So let's talk about the Pythagorean theorem real quick. So for any right triangle, we have that a squared plus b squared equals c squared. And we'll just quickly do a proof of this real quick. So we're going to use this diagram here with all of these triangles. And what we can do is find the area of it in a few different ways. First off, just by using the side lengths, we have a plus b squared is the area. And if we expand that, that's a squared plus 2ab plus b squared. And then we can also find the area by adding up the areas of the different shapes inside. So we have 4 of these triangles. That means the area of all the triangles will be 4 times half AB. And the big square would have an area of C squared. And then these two things must be equal. So the AB's cancel, and we're just left with A squared plus B squared equals C squared. So that's a pretty quick proof of the Pythagorean theorem. Okay, now we can also have some special triangles that are right triangles. A 30, 60, 90 triangle is any triangle that has the angles of 30, 60, and 90. So the ratio between the hypotenuse and the shorter leg will be 2, and the ratio between the longer leg and the shorter leg is root 3. You can see that in this diagram here. And then we can also have a 45, 45, 90 triangle. So that this triangle will be isosceles because 2 of its angles are the same, the 45 and the 45. And then the ratio between the hypotenuse and any leg will be root 2 to 1. So these are really helpful because if you have any of these triangles in a problem, you can get what the angles are or what the legs are pretty easily. So let's take a look at this checkpoint real quick. There's no answer to this one, but just go ahead and verify it on your own, and we'll talk about it in about a minute. Notice that it's talking about an equilateral triangle that has all the same sides and angle degrees of 60, and you're dropping an altitude down the middle. So go ahead and try that, and we'll talk about it soon. All right, did anyone get it? So the way we can do this is by using the Pythagorean theorem. So let's let the sides of the triangle be 2a. When we drop down the altitude, that means the altitude is at a 90-degree angle, and that splits the side in half. So this is a. And then if we just use the Pythagorean theorem to find the other side, so let's say this is b for now. A squared plus b squared equals 2a squared. So b squared equals 3a squared, or b equals root 3a. And that gives us all of the ratios that we see here. So kind of segueing into equilateral triangles and isosceles triangles. A triangle is isosceles if it has 2 sides with the same length, or if it has 2 congruent angles. So say this is an isosceles triangle here. These are the 2 base angles, and if they are the same, that means it's isosceles. And if these 2 sides are the same, it also means it's isosceles. And we also have this theorem here that says that the altitude from the non-base angle. So that would be the one at the top here. It divides the triangle into two congruent triangles. So this one will be congruent to this one. Looks like this one got cut off a little bit, but it's basically saying that the altitude that we're talking about here is also the median and the angle bisector from the vertex. So that means that it bisects this angle here, and it's the median. So these two segments that are formed here are also congruent. And if we know that two sides are the same length in the triangle, we can also tell which two angles are congruent. And as you can probably guess, a triangle is equilateral if all three sides are the same length, or if all three angles are 60 degrees. And if all these conditions are fulfilled, the triangle will be equilateral. So we'll quickly go over similarity and congruence now. So basically, similarity and congruence are two powerful tools for angle tracing. And we'll go over the definition of both similarity and congruence. So for similarity, two triangles are similar when one is the dilation of each other. In other words, the two triangles are similar when they all have the same angles. So for these two here, they're similar if this angle is the same as that one, if this one is the same as that one, and if this angle is the same as that one. And all of their sides must be in proportion. So these two sides must have the same ratio with these two sides and this other pair of sides. And for congruency, it's when the two triangles are exactly the same. So they have the same side length, same angles, same everything. So even though we have this criteria for similarity where all of the angles and all the sides must be in proportion, we don't actually have to check all of them all the time because there are some special rules we can use to find it out pretty quickly. And we'll just go over them real quick. The first one is SSS, and S stands for side. So two triangles are similar if their corresponding sides are in proportion. So if we have these two triangles here, let's check if their sides are in proportion. 4 and 12, that's 1/3. And then these two sides has 2/6, and these are 3/9. And these are all equal. So that means that since the sides are in proportion, the two triangles will be similar to the SSS similarity. As a result, we can also, not as a result, but also we can use SAS similarity. When two triangles are similar, when there's two sets of sides are in proportion, and the angle in between them has to be equal. So let's take a look at these two triangles. Again, 2 and 6, 3 and 9 are in proportion, and the angle between them, 102, is congruent. So they are similar from SAS. A stands for angle. And this is SAS helps you remember it because the A is in between the two S's. Okay, and then we also have AAA or AA similarity. And two triangles are similar if they have the same angles, but we only need to know two of the measures because we can find the third easily just by subtracting from 180. So as you can see, these two triangles are similar because they all have the same angles. Right, so this is talking about congruency. And as we said previously, their triangles are congruent if they have the same angle measures and same side lengths. And that means we can use some variations of the similarity rules to determine congruence. So similarly, we can use SSS congruence. So if two triangles have the same side lengths, then they are congruent. So over here, you can see that both triangles have 5, 6, and 8. 5, 6, and 8, so they will be congruent by SSS congruence. And we can also use SAS congruence. So if two triangles have two sides that are the same length, over here we see 5 and 6, 5 and 6, and they have the same angle, 93 and 93. That means that they will be equal. And we can also use ASA congruence. So if two triangles have two angles that are congruent, and if the sides in between the two angles have the same length, the two triangles are congruent. So over here, we can see there are two sides, 2.8, 2.8, 3.2, 3.2. Okay, sorry about that. I'm back now. um, let's resume. Right, so these two are congruent by ASA congruence. And then there's also another one called SAA congruence. And that's where if two triangles have two angles and a side length in common, then they are congruent. And the common side has to be in the same position relative to the two common angles. So let's take a look at this one where we have 5, 93, and 38. So the 5 is next to the 93, and this angle is unknown. And this angle is also unknown, and 5 is next to the 93. So that means they are congruent. And SAA congruence is actually equivalent to ASA because you can easily find the measure of the other angle. And it's generally always better to use ASA congruence instead of SAA because it can get pretty confusing at times, as we'll see in the next checkpoint. So does anyone know why these triangles are not congruent? Anyone know why these triangles are not congruent? Nancy says the side length is not between the angles. Right, so in this one, 6 is between 93 and 38, but in this one, 6 is on the opposite side of 93. So this is an example where SAA might get confusing. And that's why you always want to find the angle, the other angle here, and use ASA instead. Okay, and finally, we'll talk about HL congruence, and this is a special case for right triangles. And two right triangles will be congruent if they have a congruent hypotenuse and leg. So here we have ABC and A1, B1, C1. And it's not marked, but this is where the right angle is. And as you can see, they have the same hypotenuse and leg. And that means that they will be congruent. And we can also say that if they're in proportion, they will be similar. So does anyone know why HL congruence is true? What theorem can we use to prove that HL congruence is true? Right, Pythagorean theorem. Remember that a squared plus b squared equals c squared. So since we know the hypotenuse and leg, we can get the other side. And since the hypotenuse and legs are the same, it will be the same length. And then by SSS congruency, these two triangles are congruent. And this can be helpful if you spot this in certain problems. It can help make things a lot more simple. And we'll go over this example now with the mid segment of a triangle. So let's say we have triangle ABC. M is the midpoint of AB and N is the midpoint of AC. And it wants us to prove that the length of MN is half BC. Okay, so first, we can notice that AM, the triangle AMN, is similar to triangle ABC. And furthermore, since this is the midpoint, AM, twice of AM will be AB. So AM over AB equals 1/2. And since the same ratio has to hold, that means MN over BC equals 1/2. And that just gives us MN equals half BC. So this is a pretty interesting fact that might be helpful in solving some problems. And let's also talk about this one. Now we have a parallelogram in this example. So let's draw it real quick. This isn't the best drawing, but well, A, B, C, D. And we're trying to show that ABC is congruent to CDA. So kind of these two triangles here. And we're going to use all three of the congruences here. So first for SSS, since all sides of the parallelogram, since the opposite sides will be the same, so AB equals DC, and AD equals BC. And of course, they share this same side AC. The triangles will have the same side lengths, and it's true from SSS. Now for SAS and for SAS, we can also see that ADC and ABC are equal because they're in a parallelogram. And since these two sides are the same, again, they're congruent using SAS. Okay, and now for SAA, we actually have a transversal here. AC is a transversal. So that means that this angle here and that angle will be the same. And that means that we can now use SAA with this angle, that angle, this side, and same for on triangle ABC. And since they're all the same, we have SAA congruence. So just a few quick applications of congruency and similarity. Okay, so angle tracing is the art of using geometric tools to find measures of angles in a figure. And the most helpful thing you can do to solve angle tracing problems or any geometry problems is to draw a large, neat diagram. This is very important because most of the time you can't really visualize the problem in your head. You have to write it down. And it also helps to draw a tidy diagram because if you keep things neat, it will be easier to spot some geometric figures or relationships. And that can make it easier to see which way to proceed. And some of the things you might look for are congruent segments and angles, similar congruent triangles, right angles, isosceles, equilateral triangles, and parallel lines. So, and one other thing that can help with angle tracing is geometric construction. With this technique, we draw new auxiliary lines, or we can extend some of the lines in the diagram to expose more geometry. So some lines you might want to try drawing are parallel lines, angle bisectors, altitudes, or whatever you think might help. So we'll demonstrate with this one here. And let's pretend you didn't have the diagram and you just had this. ABC is a triangle with AB equals AC. K and M are points on AB, L is a point on AC, such that this mess is true, and you want to find the angle A. So it's pretty hard to understand, but once you draw the diagram, it's pretty clear that it's just a bunch of isosceles triangles. So let's see, BC equals CM. That means that this one is isosceles here. NL equals CN. So we have another isosceles triangle here, and another isosceles here, another one there. And of course, the entire triangle is also isosceles. So if we let the vertex angle, what we're looking for, be x, we can go through and find all of the angles and all of the isosceles triangles until we get to one of the base angles, which equals 4x. So since we know that the base angles will be 180 minus x over 2 equals 4x, we can now just solve for x pretty easily. And if we do that, we get that 9x equals 180 and x is just 20. So drawing a diagram helped make things a lot more easy in this problem. And I believe this is the last slide. So we'll take a break after this problem, and we'll start the Kahoot soon. But this is one example of drawing an auxiliary line. So In this figure, we have AB is parallel to CD, BXY equals 45, DZY equals 25 degrees, and XY equals YZ. And we're trying to find the degree measure of YXZ. So first, it helps to draw the actual line of the triangle. And then one other thing we can do is note that these two lines are parallel. What if we just drew another parallel line through Y? And that means that ZY and XY are now transversals. So we saw that DZY is 25 degrees. That makes this part 25 degrees as well. And we also saw that BXY equals 45. So that makes the other part here 45 as well. And if we add those two together, 25 plus 45 equals 70 degrees. And finally, the other part of the problem is that XY equals YZ. And that means that the triangle here is isosceles. Note that YXZ over here is a base angle. So to find that, we just do 180 minus 70 over 2, which gives us 55 degrees. So any questions about this? If not, we'll take a short 5-minute break and we'll start the Kahoot at 3 o'clock. everyone, join again. I think we're still waiting for like more wait for 3 more we're gonna start in 30 seconds. So join now. Okay. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The complement is like add up to 90. So it would have been 60 because its complement is 30. Magic is not real takes the lead. Right, it's 20. Just do some algebra with congruent angles. Don't think too hard about this one. The largest angle in a right triangle will always be the right angle. So it looks like a lot of you got tripped up there. Okay, nice. And we use the fact that there's a ST and QR are parallel and PR is a transversal to get STR. Okay, nice. Right, it's isosceles, and that means you can find the PQR, and this is right, so you can find the other parts that you subtract. think this is a pretty classic problem. But anyway, you have to remember that since they share the same side, AC and DC will be congruent, and this is isosceles. So once you find ACB, which is just 150, this part is 15. And same for the other side. That's also 15. So so the stuff in the middle will be 60 minus 30 equals 30. Uh, 6 dots takes the lead. Okay, I'll give you guys a hint. Find this angle. Yeah, let's talk about this one. So what you want to do is, oh, come on, let me, okay. This one is actually not that hard as it looks because these are all equilateral. That means this angle is 55. This angle is 45. Overall, this angle is 80. So that means this is 80. They're vertical angle. Yeah. This one is 80. This one is 60. This one is 40. So the answer is 40. Um, right triangle PQR with Q equals R. That means it's a 45, 45, 90 right triangle. PR equals 6 root 2. Okay, now we drop down this altitude. And that makes this 6. And this is 6. So the area is 6 times 6 equals 36. Yeah, PPR is a leg. Florence, does this help? Okay, well, the Kahoot is available online afterwards. So, sorry about that. I guess, I guess I'll talk about this one. Hang on. Okay, so first we'll look at this part where the area of the larger one is 16 times the smaller one. That means the side length of the larger one is 4 times the side length of the smaller one. And that means that they're in a ratio of 4 to 1. So the perimeter of the smaller one would be 45 over 4 plus 1 equals 9. So it has a side length of 3. And the larger one would be 27 with a side length of, 36 with a side length of 12. And you can verify that that works. Okay, and then for the area of the larger triangle, use the formula and get 36 root 3. Okay, nice. Oh, um, huh. Okay. Hopefully I didn't mess up the answer for this one. Um, let's see. So, um, okay, so first off, we notice that these two triangles are similar. ABE and CDE. They are similar. And that means that their heights are in a ratio of 2 to 3. Like their bases are in a ratio of 2 to 3. So that means if we let the altitude of the smaller one be 2x and 3x be the top one, this is 5x. So BC is 5x in total. And we're looking for EF. So now we take a look at triangle BDC. So notice that BEF is similar to BDC. So the height of BEF is 3x over 3 over 5. And then we also compare EF to DC. EF over DC. So EF over 100. So that means EF is just 3/5 times 100 equals 60. Any questions about this one? Okay, let's move on now. Oh, no one got it right, so there's no change in the leaderboard. Second to last problem. right, this one was not bad. Just some angle tracing with the equilateral triangles. Move on to the last question. Nice. I hope this problem helped bridge a few gaps in your understanding. Congratulations to our winners. 53% correct. That's improving. This problem is not great, but it's a good start.